No, stop. We're on. You almost saw Larry freak out. But we caught this at the tail end of it. How are you, Larry?
I'm doing just fine.
Excellent, man. So, Win 7, RTM has happened.
We're done.
Excited. You're finished. You're good to go. So, hey, we had a great talk with you at PDC.
Yeah.
And you gave us sort of a high-level overview of what's new in Windows 7 audio system. And today we have another familiar face. We remember you from the Vista. Introduce yourself.
Elliot, Omiya. I'm an architect in devices and media on the audio team.
Excellent. And a very new face here.
Hello, Frank Yerrace, a principal developer on the audio team.
Excellent. So let's talk about what are we going to talk about? Let's dig into the architecture today, right? We want to go low. We want to go deep.
Yeah. So it's interesting about audio because audio is this thing you never see, mostly. You just hear it. So we made a lot of improvements that are below the covers and talk to the whole concept of attention to detail. So we'll get into a lot of the specific topics, but we made changes to the audio engine. We added a new feature called Capture Monitor. We support HDMI audio. Most people think of HDMI as a video technology, but actually there's an audio component to it. We implemented ducking and some other things that I'm sure we'll get to, and other things that we'll probably forget. So,
excellent. So, Frank, you haven't been on. Tell us a little bit about yourself, because you're new.
Yeah, I've actually been, new to this,
yes.
but kind of old to audio. I've been involved in Windows audio for ever since I came to Microsoft, which is 16 years ago.
Wow.
Yeah, so initially worked on Windows 95 was my first project here. And,
excellent.
Yeah.
So when we think about Windows 7, I think one of the things that is crystal clear is that it's a super efficient version of Windows and on many levels. Can we talk a little bit about efficiency at the audio level?
Sure. So okay. So on that topic, let's start with what we call pull mode engine.
Excellent.
So we implemented a new audio engine in Vista, and you can search for the Channel 9 video we did at that time.
Yep.
And that was a big effort to take the audio engine out of kernel mode and put it into user mode. Now we have a system that we could build upon and improve. And so what we wanted to do was use a technique we will describe in a second called pull mode, which is to improve reliability and consistency, reduce power, and reduce latency latency in the system. So basically, when we say pull mode and push mode, that's a really common computer software term. In this case, what it means is push mode means that we'll run a timer, and the audio engine will wake up every 10 milliseconds. It's variable, but let's say that's the normal rate, and process some audio and then push it down onto the kernel streaming audio device. This has a couple of different problems. Problem number one is you must run a timer resolution on the system very low, typically 1 or 2 milliseconds, which means that the process is running full tilt all the time. That's bad for battery life and power consumption. So we wanted to reduce power consumption.
Right.
The second thing is that there's this problem with aperiodicity, which is that the timer on that and the timer that the audio systems run on will be different. And so what happens is we will wake up out of step with the audio cadence. And so we implemented this thing called pull mode, which means that the audio system will signal to the audio hardware will signal to the audio engine when to wake up and do work. And so it's event driven or pull mode.
Nice.
And so we implemented that for what we call exclusive mode audio in Vista, but now what we did is we took the bottom edge of the audio engine and also made it basically an exclusive pull mode client. And so all of the modern hardware that uses HT audio drivers, either our class driver or third-party OEM IHV drivers, will signal events when a certain thing happens in terms of when the audio has been consumed and a buffer is available to be refilled for audio to be played in the future. And then we will do that. That has a couple of immediate benefits that are obvious. One is that the regularity of the engine is very good. Typically what happens between the KE set event that's done in kernel mode and that driver and when the engine wakes up is just a few microseconds typically, because we use MMCSS, which I'll talk about some changes on that in a second. So that thing will wake up very, very quickly after that set event. And the other benefit of that is since that interrupt and deferred procedure call in kernel mode is very regular based on the consumption of the DMA buffer memory and the audio codec, we get the engine running every 10 milliseconds at a very, very low standard deviation from the nominal 10 millisecond rate.
While we were testing out this test, while we were testing out the feature, one of the things that we asked ourselves was, well, A, how much benefit are we going to get from it, and B, what, does it actually work? And so we actually had one of our testers build up a test app that basically wrote sounds out of speaker and then ran it through a loopback cable into the line in, and they measured the signals as it was being transmitted and received and correlated the times and everything. And what they found was that the engine latency, and this is round trip all the way through a USB audio device, so it's pretty close to our worst case scenario, went from being about 85 milliseconds with a standard deviation of almost 10 milliseconds down to 53, 35, something like that. So dramatically reduced the latency of the engine. And the standard deviation also dropped down to 3 or 5 milliseconds. And there's actually some question about the measurement. That may have been a test artifact. It may have actually been finer than 3 to 5 milliseconds of latency. So the engine has become dramatically, not only lower latency, but dramatically more regular. More regular actually gives us really couple really cool benefits that you don't always think about. The first is that being more regular means that, well, frankly, we're waking up less often. We're not doing nearly as much, and that means the system can go down lower power states more often and more accurately. The other thing is that for a lot of applications that depend on low latency audio, and that means things like voice chat and Skype, instant messaging and phone communications, these apps actually really care because they have acoustic echo cancellation algorithms that rely on the fact that the amount of time between what you're saying and what's heard back on the speaker as it bounces off their servers, they rely on that time being very, very short. So by squeezing 20 or 30 or 40 milliseconds out of the amount of time the audio engine runs, dramatically improves their ability to make their algorithms and tune their algorithms and make their experience better. And that's sort of goes towards what Elliot was talking about earlier about this attention to detail and polishing, and it's not 20 milliseconds less latency. It doesn't sound really like exciting, but the overall result, the end result that you get, is quite surprisingly how much better it is. It does actually really improve things. So.
Yeah, the real-time communication team at Microsoft worked closely with us on this latency improvement, and they talk about a budget, and I don't think I want to quote the exact number, but they have a certain budget in terms of numbers of milliseconds in which they can round-trip the network and get everything through their internal audio engine and through the audio stack. And a lot of times in kind of less than optimal networking conditions, think of it, you're talking to your parents in Europe or the Far East when the network round trip takes a long time. The audio engine latency makes a bunch of difference because it means the difference between you have a phone call and you don't, whether or not you actually took up this budget. Because if you go over that budget, the phone call totally fails. And so actually latency reduction is really important in terms of it makes a difference on whether the phone call, especially in long distance VoIP scenarios, is actually successful or not.
So how did this latency reduction sort of manifest itself in code, right? I mean, what did you do? What did you write? I mean, let's talk about the algorithm changes that had to happen, right? You mentioned you added more something to something else, but continue. I'm just kidding. But can we talk about a little bit more of how you guys actually composed this?
Yeah, well, primarily it was changes in the audio engine and in the drivers. The engine, this is primarily EHO's area, but the engine was modified to listen to the events in shared mode as well as exclusive mode. EHO mentioned that we had this implemented for exclusive mode in Vista, and we enhanced that to also support shared mode now in Windows 7. So the engine would use these pull mode events, even in shared mode. And whenever the events would be signaled, that was just an indication to the audio engine that it was time to send another buffer down to, or fill the next buffer for the audio driver to consume. And the buffers are, this is probably mentioned in the Channel 9 video for Vista, but the buffers are directly mapped from the audio driver to the audio engine, so there's no submission of an ERP in order to get that next buffer of data down to the driver. It's just a direct mapping of the DMA buffer. So when the engine fills that buffer, it's directly consumed by the DMA engine of the audio driver.
Excellent.
Well, one way you can sort of think about this is that in Vista, we added the ability to the drivers that the drivers would be able to wake up an application that was on top of them and say, hi, please give me the next packet of data now. And they could wake up an application. Now, we really only supported that in exclusive mode, and we intended it for the use of pro audio applications that really need to have very, very, very fine latency, as close as possible to the hardware. So what in the audio engine, when it was running in shared mode, when you were mixing with other applications running, the engine operated in a mode where basically every 10 milliseconds it went and asked the driver, so how much data can I give you? So instead of the driver waking up and saying, give me the next 10 milliseconds of data, the audio engine would wake up and say, hi, can you take another, can you give me 5 milliseconds of data? Or oh, you want 5 milliseconds? Okay, I'll give you 5 milliseconds. Oh wait, you want 15 milliseconds now? Okay, I'll find 15 milliseconds of audio data and hand it to you, or whatever it was that the driver had available at the time we happened to wake up. Now the driver's telling us, saying, okay, give me the next 10 milliseconds, give me the next 10 milliseconds, or 10.8 milliseconds, or whatever the driver decides is, whatever we negotiate is the best frequency to wake up with the driver. We wake up and we give him just that amount of data, and it means that it basically simplifies and it regularizes what happens at the driver. So we changed basically the very bottom edge, and then there were a number of changes that bubbled out as a result of that up through the engine to make that all fit together. So
Excellent.
So before we finish this topic,
Please.
let's talk about MMCSS. So that's the Multimedia Class Scheduler system, and it's the system that was built in Vista that allows us to run the audio engine at a very high thread priority without compromising the system. So basically it's this 80-20 rule. 80% of the time we are able to run at a high priority, and 20% of the time we're at priority 6. So we don't actually run. And so this was actually done with a 1 millisecond timer resolution and a very high priority thread in the AVRT service, the MMCSS service, to make sure that it could take care of this 80-20 accounting, which absolutely depended on a 1 millisecond timer. And one of the things we wanted to do throughout the entire multimedia stack was remove as many calls to set the timer resolution to 1 millisecond, and that's primarily to save battery power. And so we implemented the multimedia side and the kernel team what we call lazy MMCSS. So now MMCSS will not set the timer resolution to 1 millisecond except when it wants to take us down to the 20% price 6 thing. Now, it's really important for them. Once we go down to that 20% priority 6, we must get back up to the higher priority, which is typically above priority 15, at the end of that 2 millisecond or that 20-second period. So what they will do is when they notice that the system load is getting above 80% and we shouldn't be running again at priority at a high priority, they will then set the timer resolution to 1. Once they achieve that, which may take several milliseconds, then they will take us down to 20%. Run us for 2 milliseconds at that, take us back up, and then return the time resolution to the system default. So basically what this means is a system that's not at load will always be running at the default timer resolution, which could be as high as 15 milliseconds, which allows a much better power profile on the machine. If the machine's under load, then it will be running at a 1 millisecond time resolution around 20% of the time.
Excellent. I mean, now power management is really pretty impressive in Windows 7. I've actually talked to those guys. And so I would be curious as to what happens with you guys when I decide to change my configuration to power saver mode. I mean, what sends obviously a signal to you guys? What do you do in that circumstance, and does it affect my playback? If I'm listening to music and I go from high performance to save power mode.
It actually normally doesn't. The one place that it might affect you is the HD audio spec specifies this thing we call low power mode. And so what a Win 7 IHV audio driver can do is opt into low power codec, and that allows that codec to work in that lower power state and potentially be turned off when there's no audio streaming. But basically, once you start streaming audio, there's not much effect from that setting. What we basically did to help that is during the entire time you are running audio, regardless of what the power setting is, we will try to be more efficient with the time resolution and the power. And so that works on battery, that works on AC power, and so we can try to consume less power regardless of what your power profile is, which I think is the best of all possible worlds. It helps all the scenarios and helps us save polar bears or whatever it is that using less power.
It might be worth mentioning just briefly that there's HD audio engineering chain ECRs that define how the HD audio codecs should indicate that they support the low power modes. So it's important that the newest codecs pay attention to those ECRs, which are modifications to the HD audio spec to properly implement this so that our class driver can support the low power modes on the codec and the controller potentially.
Awesome.
So I think that's a pretty good and complete talk about the engine changes. Maybe we can...
well, there wasn't any whiteboarding though, so you leave me to kind of say, you said something about something. I was just playing, by the way, for the record. I wanted to get Frank to talk because he has a lot to say. So yeah.
There might be one more comment to make about that real briefly is that the custom drivers that want to support pull mode do need to indicate support for this via an INF entry. Even if they support the necessary interfaces in the driver, we won't automatically use them in this new pull mode. So when they have their custom INF that they create for their custom driver, they need to indicate in that INF that they support this. And the reason was that even though these interfaces were defined in the Vista era, they weren't well exercised because we didn't use them in shared mode. So we found, our experience showed that there were lots of issues when we started exercising these interfaces. So we didn't want to just use them across the board by default. Instead, the newest implementations in their INFs need to indicate that they properly support these interfaces.
And they're required to for logo.
Yes.
Yeah, and they're in the logo.
That was going to be my next comment, was exactly that, was that Win 7 logo devices will all support this. So if you've got a machine with a Win 7 logo on it, it will be running the audio engine in the low latency mode. It's only the Vista logo drivers that have not been updated. Those will still run in the older mode, simply because we can't reliably, again, we're not going to break end users' audio solution. We're just not going to break their audio, so we made this feature optional, and the drivers have to say basically, yep, I'll do that. I'm good with that. I can support that. We're good. And so it's a requirement for Win 7. It's optional for Vista. Our inbox class driver, so if you're running with the built-in class driver on your older audio hardware, it'll work just fine. Because our driver does support, obviously, this pull mode engine.
So maybe one last war story on this topic.
Let's do it. War stories are great.
So the war story on this is that XP era audio devices implemented a spec called AC97, and these are what we call standard streaming devices. They don't map DMA memory up to user mode, so there's this thing called an iOctal, I/O control, and that's a way to get data from user mode to kernel mode. And so there's this thing we call iOctaling the driver. And we originally wanted to run AC97 in pull mode, and we actually did implement that, and I had this 5-year-old 512 megabyte Dell machine in my office. That's my favorite test machine because I ran Windows 7 through the entire cycle on a 512 megabyte machine, and it actually worked pretty well.
Yes.
Cool. So that's one thing, and it also was AC97, and we have to be backwards compatible. We have this kind of double-edged sword because we run so well on the older hardware. More people are willing to run Windows 7 on that older hardware. And so we're going to see the Windows 7 audio stack running on AC97. And it worked really good in my office. And then we deployed the pre-beta inside of Microsoft, and we just started getting all kinds of reports of crappy audio. And basically, we could not reliably run pull mode on AC97 across all of the drivers and all of the codecs and all those things. So close to beta, we made a decision to switch that back to Vista mode. So it's like kind of the best laid plans of mice and men sometimes go awry, and that was one of those ones where we intended to run that in pull mode, but then we didn't, because basically it didn't work across 100% of the hardware.
Absolutely, and Windows being so general purpose really needs to.
Right.
So where should we go now? You want to talk about ducking, or you want to talk about...
Let's talk about capture monitor.
All right.
Capture monitor's my baby.
Is it?
Yes.
Excellent.
It was honestly one of the most fun features that I've ever worked on, because it's just cool. Capture monitor was actually the idea behind the capture monitor feature was that one very, very popular feature in the XP era was the AC97 hardware had this thing called hardware loopback. Basically, they would literally run a wire from the from the microphone input through to the speaker. I mean, they put a volume control on it, but it basically just was a wire. It was an analog loopback, and the idea was that you could plug your portable media player into Windows, and you could plug your speakers in, you could listen to your portable media player, or if you had a microphone, you could do karaoke or whatever through the existing audio hardware. The big problem with that is that while it was popular and a lot of people liked the feature, it was expensive to build. And as a result, the IHVs who had originally provided support in their hardware removed that support. They decided that it wasn't the value of the feature wasn't enough to justify the cost of the actual hardware to implement the feature. So we put it back. And that's what the capture monitor feature is. And the capture monitor feature basically is it's a little chunk of code that runs inside the audio subsystem that basically, if you enable it, and it has to be turned on, you have to turn it on, but allows you to plug in your portable media player, and you can then listen to it on your desktop speakers. I do that all the time in my office. So it's a little feature, but it's really fun, and it was really fascinating building the actual playback engine. I learned a lot about how a lot of the architecture about how you actually use the audio APIs for it, because while I'd been working on volume and all these other things, I'd never actually worked with the actual streaming part of our audio stack, and it was a fascinating learning experience for me.
So, and when Larry says we put it back, he doesn't mean we put the analog electronics back.
Yeah.
He means that we provided a replacement for it.
Yes.
Larry went and wrote this software that captures from the inputs, whether it's the line input or mic input, or usually the line input. We don't recommend the mic input.
Really
and
don't
plays it
recommend
back
the mic
through,
input.
plays it back through the speakers.
Yeah.
And that totally replaces the analog electronics, allows reduction of hardware complexity.
It also now works with any audio hardware. So if you want to plug a USB headset in, it works fine. It will work from any device to any input device to any output device. Now, Frank's right. You don't want to plug it into a microphone port because, first off, mic ports clip easier than line in ports. I'm not 100% certain the electronic reasons for that, but there are. But they clip more, so the sound quality is worse. But more importantly, if you actually are using like a microphone input on your laptop, you will get feedback, and it's really disruptive when it happens. It hurts. Yeah.
So I can't use my laptop for karaoke, man?
Yeah, you can if you plug a microphone into the microphone jack.
Yeah.
But typically the microphones on laptops are too close to the speakers, so they get into a feedback loop. Actually, it was funny. We have a little USB audio device that has multiple inputs and output connectors, and we plugged it. It was another war story. We plugged the USB device in, ran the input to the output, and the output is actually and then we ran the capture monitor, and it set up this just totally bizarre reverb effect where you turn on the capture monitor and you go ding, or you made a sound, so you make the Windows go ding, and what actually came out your PC speakers was ding 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 ding. It was really freaky, and it was like when one of the testers pointed out to me, I set up the thing in my office and went and did it, and it was like so weird and freaky. Grabbed Eho from across the hall. Come listen to this, and anybody I could find in the hall was like, "Come listen to this, just weird." It's an artifact of just the way the hardware ends up working, the latency of the various pieces in the hardware, and how it feeds back in. So it's nothing I would actually even dream of suggesting anybody do, except as a wow, geeky, fun thing. But anyway, whatever.
So we've been calling this feature capture monitor. I think in the user interface it's actually exposed as listen to, right?
Yeah, listen to is actually the official
So
feature.
in the sound control panel it's called listen to.
There's a list tab called listen. You open up an input device.
Okay.
There's a tab called listen. You click on the tab and it allows you to turn on the feature and set it up. We were talking about power, by the way. One of the things that the capture monitor feature, that the listen to feature has, one of the options actually is that when you go on, if you're on a laptop, when you go on battery, we turn off the capture monitor. We actually have logic in there that basically says, oh, this thing does consume audio. We're capturing, we're streaming. That prevents your machine, if you're using it, you're streaming audio. So we're running at a somewhat higher power consumption state. So if you're on a laptop, you can actually configure it so that when it's on battery, it shuts down, so it doesn't consume the power.
So one of the questions I would ask, just before we move on, because I know we have to, is in terms of the higher level applications, say like, what's a good example? Zune, the Zune client. How about that for Windows? What can they do? Have you guys exposed something in your API that would make it easier for them to do things that doesn't adversely affect my battery life?
So the main thing that shared mode applications can do is use what is actually a Vista feature, and actually we did this also. I'll explain how in a second, to use what's called shared pull mode. And it's analogous to the event-driven mode that we do at the bottom of the engine that's close to the audio device, but this is up at the upper end of the audio engine where the client application is providing audio samples. And basically after the engine runs its 10 millisecond processing period, it will signal event to the application that they provided the event handle for, and then it's basically fill now. And we call that shared pull mode or shared event-driven mode.
So the documentation calls it event-driven.
Event-driven, yes, that's true.
Okay.
So pull mode is actually just this internal moniker that we put on it. And one place we did this is the Wave API, Wave Out and Wave In on Vista runs a pretty large buffer and was push mode, ran on a timer. And one of the changes we made in Win 7 was to put Wave on event-driven mode or pull mode. And the latency went from way over 100 milliseconds to 30 on that change. And so that's the main thing people can do is, once they do that, they don't have to run a timer, they don't have to run time begin period 1 and other evil things that are bad for the battery and the planet. They can just be signaled when it's time for them to run and provide audio samples. So that's the number one recommendation I would make. We have some other things about when we talk about ducking and when we're going to do that on things that they can do. But in terms of streaming, that's the main thing, is use shared pull mode.
Yeah.
Cool.
A quick war story on that one. I was working on the samples, the SDK samples, and I wrote the exclusive mode event-driven sample first. And so I wrote the sample and tested it, and it worked great. It was wonderful. And so crystal clear, played the sine waves, it was wonderful. I got around, took the code and altered that code so that it would run in timer-driven mode. So turned it on, started running. It was horrible. It glitched like crazy. It was horrible, horrible, horrible. And I'm like, what am I doing wrong? What am I doing? I'm using MMCSS, I'm doing this, I'm doing that. Everything should be working. I run the app on Windows Vista. It works great. I run it on Windows 7, it doesn't work. And I'm banging my head against the desk, trying to figure out what I'm doing wrong. And it all of a sudden hit me. I didn't call time begin period of 1. This app was running at a 5 millisecond latency. On Vista, MMCSS, as you had mentioned, set the timer to resolution to 1 millisecond. So on Vista, it was running time 1 millisecond, and so I didn't notice. So because of the side effect, the timer was running at a very low resolution, so I was waking up the system more often. So when you try to do this timer-driven stuff, especially if you're low latency, if you're an event-driven, you can dramatically reduce your battery life because you're only being woken up when you absolutely need to. When you're in timer-driven mode, you're waking up whenever you want to, and if you want to be low latency, like you're running in exclusive mode, you have to set that timer resolution down. Otherwise, you're not going to be able to stream audio properly. So, the moving to event-driven is a huge win, and it also dramatically reduces the complexity of your coding. Having now written the samples for all of these, the event-driven stuff is just so much simpler to work with.
Interesting. And it's just like typical events, right? I mean, you have a handler or a
Yeah.
delegate or whatever. I mean, it's like, I was
Set
wondering
events,
if it would be
like-
interesting, or you're familiar with the observer pattern, right?
Yes.
Like reactive programming. Is there any correlation between, I mean, that could be kind of interesting applied to the audio world, no?
It is, yeah, it can
Yeah.
be. We just call it event driven because we're so close to the lower end of the operating
Sure.
system, and so we just deal in event handles and set event and those sorts of things. But of course, you can build any of those interesting patterns on those low level
On top of
primitives,
that,
and that's
absolutely.
what we've done.
Very cool.
So I think at this point it'd be really great to get Frank to talk about
Yes.
default device heuristics.
Oh, yeah, sure.
And that can lead to both ducking and stream direction topics.
Cool.
Yeah. All right. Maybe I'll go to the whiteboard.
That would be great.
Let's go to the whiteboard.
Finally.
We haven't done the whiteboard yet. We gotta
I
do the
lost
whiteboard.
money. I had a bet Elliot would be the first one up there. So, all right. Well, Larry
share
can
the
lend me a
winnings
few
then.
bucks. I'm just kidding. I'm just kidding.
So
All right.
The default device heuristics are all about making sure that any moment in time, the correct device, whether it's an input device or output device, is selected for general purpose playback. So there, in Windows 7, we introduced a second kind of default. So first we have the regular, what we call the console default device. But now we also introduce the communications default device. And as I said, at any given moment in time, the system maintains a mapping from those concepts to some actual physical device that you have. I'm a terrible artist, so I'll just write them out. Speakers, headphones.
See, I'm a terrible artist, but it's never stopped me from drawing, grabbing pictures on a whiteboard.
I'll even put in headset. And there's between headset and headphone. A headset is more like the little Bluetooth earpieces that people use. So the system maintains a mapping from each of these defaults to one of these. So typically in this scenario, console default would point to, oops, I actually got that wrong, point to your headphones, and the COM default would point to headset. And the idea is that headset is more useful for communication scenarios. The headphones are more useful for regular general purpose audio. We call that console.
So why wouldn't it be the speakers in that
So
case?
in this case, I pointed to headphones because when I draw this, I'm assuming that headphones are plugged in through a jack detectable connection, meaning it's either an analog jack that implements jack detection. And by jack detection, I mean the system can be aware of whether something's actually plugged into it or not. Or perhaps Bluetooth headphones, we know whether those are actually connected or not connected at any given moment. If it's connected through one of those mediums, we will prefer headphones over speakers because we assume that the person plugged them in with the intent of actually using them. And when they unplug them, then this mapping automatically reverts back to the speakers. So if those are disconnected or unplugged, the mapping reverts back to speakers.
Mm-hmm.
So the idea is that we have this algorithm that we'll just call the default heuristics, that every time there's a change here in the set of available devices, these heuristics run, and they will reprogram or reassess what those defaults need to be after that, as a result of that change.
Nice.
And there may or may not be a change in the defaults, depending on what went away, right? If these headphones were plugged in, and the mapping is to the headphones, and you remove the speakers, there's actually no change affected there, right? But if you plug the headphones back in, then it will remain mapped to the speakers. So let me rewrite that out. Headphones, rather.
I've also noticed that if you, because I ride the bus a lot after work, so if you I mute the speakers as well because I don't like to hear all the sounds all the time. But I mute the speakers and then put my earphones in and they work, I mean, as you'd expect. I pull them out and it's still muted, which I appreciate.
Right.
Anyway.
Yeah, so we, of course, maintain different volume and mute settings for every individual device. So if you left those speakers muted, they'll stay muted whether we're playing audio to them or not.
Excellent.
So why do we have a communications default?
So the communications default is useful for if you're running...
You already know
Thanks
the
for
answer
asking.
to that. Wow,
Is that what they call a
question.
leading question?
Yeah. I mean,
That was a
You should be behind the camera.
yeah.
The communications default is useful so that when you're running applications, typically VoIP applications like Skype we mentioned, and Office Communicator, Live Messenger, and you want to use those applications for voice communications, VoIP calls, we'd like those applications to begin using these defaults, the communications default, because we want the system to identify what we think is the best device for communications at that moment. That would save the user an additional setup step when he installs those applications, or configuration step. As most people know, most of those applications have some UI to select what device to use for their audio playback. So out of the box, those devices can begin using the system communications default. They can still have that UI to override it if they wish, but they can use that default out of the box and save that one setup step. So if you're running that application and you're running Windows Media Player, say, or any other media player at the same time, Media Player would be playing to your speakers. Let's take the headphones out of the picture for now to make this more typical. The Media Player, let's draw that out. Windows Media Player will typically stream to your console default, and I'll just write VoIP instead of naming a particular app. Will typically stream to your COM default. And
Both ways, right? It'll have both a microphone and a
yeah,
an
headset
output.
typically has a microphone with it, and we maintain defaults for both inputs and outputs. The capture is more relevant for communication scenarios, but it can apply to console as well. So if you're using both of these applications at the same time, the Windows Media Player will stream to your desktop speakers like you'd expect. Your VoIP application will stream to your headset so you can have your conversation. And this kind of leads right into the next topic, which is ducking. When this stream starts up, suddenly we'll invoke the ducking feature. You want me to go into that, or do you want to?
Actually, before you get to ducking, let's talk about stream redirection. Because
yeah, good idea.
That's actually maybe closer to the default device topic, and then we can branch into ducking.
Sure, yeah. So with stream redirection, what that means is anytime an application has opened a stream on a default device, and let's talk about console default in this scenario.
Okay.
And that default suddenly maps to a different device out of your set of available devices, this stream will automatically be redirected to that new default without any action being taken by the application. So if I suddenly connect some headphones, let's plug these in again, kicks off these heuristics. The heuristics decide, well, let me change what this points to. So this now points to the headphones.
Great.
The stream that was playing to the speakers is automatically redirected to these headphones without the application having to do anything. Now, I'll mention this caveat though. It does depend what API is being used here. Streaming, of course, goes through an API layer. So there's some APIs where this redirection happens automatically, and that includes Media Foundation, Direct Show, Direct Sound, Wave, and those are the most common, that might be the complete set of higher level audio APIs. One API that it does not apply to is our newest lowest level API, which is either called Wasapi, some people call it Wasapi for Windows Audio Streaming API or Session API? Session API.
There's some controversy with that.
Everyone gets correct. Also, people just call it Audio Client API sometimes because the core interface for there is iAudio Client.
The SDK documentation actually calls it the Core Audio APIs.
Core Audio APIs, yeah.
Which is kind of weird because OS X has a similar concept.
Yeah.
And I find that kind of confusing, but...
So all these are names for the same thing, but the point is if you go to this, which is now the lowest level supported audio API, you don't get the automatic redirection. But these are the most common APIs in use today, and if you go through those APIs and you open the stream on the default, you'll get that redirection automatically.
So how does that work? How did we do that?
So we had to actually do it in every single one of these APIs. There was no one point below these APIs where you can just implement redirection. So every single one of these, we had to go into those APIs, modify the logic that is selecting, that selects the default device, register for notifications that a default is changed, and when it receives that notification, it would have to suspend that current stream, destroy various objects related to that particular stream, recreate various objects for the new stream, maintain states such as position information and all that kind of stuff, which is all, how you do that is going to be specific to each of these different API layers. But it was a fair amount of work, and Iho and Adil,
yeah.
Adil Islam did a great job of making that work for each of these.
Well, and Michael
Although I
did
think
the
Michael
work.
did it.
Michael
Michael
did-
Savage did it for Media Foundation.
Right.
I think Direct Show as well, didn't he?
No,
Direct
actually,
Show, Direct
Direct
Show got
Show.
it for free from Direct Sound.
That's right.
Yes, oh, that's right.
Yeah,
Yes.
Direct Show is layered on top of Direct Sound for its audio rendering, so Direct Show got it for free once it was done for Direct Sound.
So what you're saying then is stream redirection is really just creating destroying current stream, getting all the information you need, and creating a new stream, pointing to a new place, as opposed to taking the current stream and just redirecting it to a different output.
Well,
that's
so the former is
result of
the
choose.
former is the implementation detail of the latter, which is the effect.
Right.
And so we take that stream, we suspend the flow of data on that stream, we destroy the old one, or it got destroyed underneath us actually, because we registered for a session notification, and typically what happens is the session notification says, your session's done, it's gone. And then we wait around for a short period of time, typically 500 milliseconds, to see if a new default device came online. And typically in the scenario that was described it will, and then we'll just recreate the stream and start it up. We were really worried about having AV sync problems after we did a stream switch, but it turned out that just simply suspending the stream, stalling the audio clock, stalled the video, and we could take a relatively long period of time, several hundred milliseconds typically, to switch the stream to the new one, start everything up, and then we would have really good AV sync afterwards, because every clock was stalled during the switchover.
Right. So there's going to be a glitch,
Yeah.
right? But it's typically minor and it's acceptable. I think people would accept the fact that if I do something physical to my system, I plug in some headphones and the stream moves to that, a minor hiccup there is going to be,
Sure, or if
expected.
you drag a playing video to a new monitor, for example.
Right.
Same
I
idea.
do that a
yes.
lot, and I experience that.
And in fact, in the case of dragging a video to a new monitor, it is an almost identical experience. The render graph is torn down by the code that's actually doing the video rendering. It tears that down and then it reestablishes it on the new monitor, and so which is why you get the exact same sort of glitches and tearing and things like that. So
Sure. Now, is that the only way to implement it, or is it just where we are today with our current level of
Well,
technology?
I don't know if we're supposed to say stuff like this,
Don't
but,
say stuff
but
like
it's
this.
the only way we could figure out how to do it. So I'm not claiming that it's the only way to do it. It was the only way that we could figure out how to do it.
It's great, man. It's a super hard problem. Nice.
it was a very hard problem, and there were some. We had some internal discussion about ways of implementing it, but it turns out that this really is, honestly, from where our technology is the best, because it's the most reliable, the simplest, the one with the least impact on the applications.
Sure.
And,
Yeah, the big debate was whether to try to implement it as part of the API layers versus evangelize all the various interesting application developers to start implementing stream switching in the applications themselves. Because when these default device mappings change, whenever this pointer moves from one device to another device, a notification is sent out that applications can listen to and register for. In fact, the implementations within these APIs listen for those notifications. So in theory, the applications can listen to those notifications and respond to those notifications themselves, suspend the stream that was going to the old device, recreate the stream on the new device. And from the end user's point of view, it'd be the same end result. But by doing it in these API layers here, we're able to just effectively retrofit a bunch of existing applications with this new feature.
That's great, and it makes sense. It should offload onto the experts like you guys.
Yeah.
That's good thinking.
Right.
All right.
So one more thing on stream switching before we probably move to ducking, since we're running short on time, is this is equally applicable to the communication scenario. So the scenario I would describe is you have a VoIP app like Windows Live Messenger or Skype app, and you happen to have the communication default input on the built-in microphone on your laptop,
Okay.
which is not a very good thing for VoIP applications. You want to use a dedicated headset if you have that available. So what
Yeah,
happens is if the communication default input is the mic on your laptop, and then you plug in a dedicated headset with both an earpiece and a microphone on a boom microphone on it, the communication default will switch to that headset. And even if your call is already in progress, you already picked up the virtual phone call from your mom in Singapore, and the communication started, it will automatically switch to that headset. And so it's equally applicable to the VoIP scenario, and actually is maybe even arguably even more useful in that scenario, because you might not normally have the headset plugged in. Because you weren't
a lot of people
expecting that
consider
call.
a lot of people consider that the more interesting scenario, because you'd imagine starting a call on your sort of virtual speakerphone, desktop speakers and mic, and then deciding, gee, I want it to be more private. So you want to just plug in that headset, whether it's USB or power on your Bluetooth headset, and have the call just automatically direct to that. To
Absolutely.
device.
Yeah. By the way, for ISVs who want to implement the stream switching suite feature in their application, which they can if they want to, the new SDK samples actually include some code examples of how to implement the stream switching feature for applications. So we actually there is sample code now available, or will be available when the SDK is published, that actually has that in as a part of the SDK.
Excellent.
Also wanted to mention, Frank touched on it, but this is only available if you choose the console default. If you say, I want to go talk to those speakers, if your app says, I'm rendering audio to the speakers and the speakers get unplugged, we're going to fail.
Yeah.
And the reason is because you chose speakers. And we're not going to try to second guess your choice. If your app says, I want speakers, we don't know why they chose speakers, but they did. So we're going to respect that choice, and we're not going to try to change it under the covers.
Right.
Sure.
So graphically, that would look like if a VoIP application was directly rendering to the speakers and directly using that microphone, rather than going through the defaults here, then when these default mappings change, that doesn't affect these streams that are playing directly to these devices or capturing directly from these devices.
Understood.
If they're streaming to the default and that mapping changes, then the stream will automatically go to the new device.
Because they don't call the default heuristics that you're mentioning down there?
That's
or-
right.
Because they didn't ask for the default, which is determined
Sure.
by the heuristics.
Absolutely.
Right.
So don't do that, apps.
That's
Yeah,
right.
so the
Yeah.
developers in the audience, there's IMM device enumerator, get default audio endpoint, is that right?
Yes.
Yes.
Is the thing to call. If you call IMM device enumerator,
Get device.
get device, you will get none of the stream switching behavior. Nor will you get
Some of the ducking.
some of the ducking. Actually, is that wired to default? It's really
Yeah,
more.
It's wired to communications.
to invoke ducking, right?
That's right.
So, and let's talk about ducking.
Sure, yeah. Do you want to?
Actually, Larry, why don't you
Everybody ducks.
go to the board and talk about ducking?
Okay.
Cool.
And all
But
this.
so that means that EO doesn't ever get to run the board?
No,
Or-
he has to
wait.
go to the. You
have to
go
get Eagle on the
before
board.
we leave. You can draw out to us what sound really is. What is sound?
sound.
What is it?
Squiggly lines on this board. Okay.
right.
So, ducking. So, the way I like to think about ducking and talk about ducking is actually in terms of my car, which has a Bluetooth audio system built into it. And when I'm listening, when I take a phone call in my car, if I'm listening to a CD, the CD pauses. When I'm listening to, when I get a phone call in or when I activate the voice system in my car, it mutes the audio. You can't hear what's playing on the radio. Ducking feature is about building that kind of a feature into Windows and enabling applications like these VoIP applications and the Windows Media Player applications. It enables them to take advantage of that feature. And the way we do this, and I'm actually going to work right off of this picture. So when the VoIP application starts talking, and it's VoIP, instant messaging, doesn't really matter.
Sure.
He talks to the communications default device. What that does under the covers is it activates a piece of code inside the audio policy engine called the ducking manager. And when he starts streaming to this default communications device, the ducking manager wakes up and says, oh wait, hold on, someone is starting to stream on a communications device. Are there any non-communication streams, so streams that are going to the console default or streams that are going to an explicit device? Are there any of those streams running right now? And if there are, it first says, well, does the application want to be notified about it? And if so, it tells the application that this communication stream has just started. And the next thing it does is it says, okay, I'm going to go to every one of these streams that's running, and I'm going to shut it. I'm going to apply a policy. Now, the policy is determined by the user. There's actually a communications tab that lets you determine what that policy is. Now, the policy could be do nothing. The policy could be reduce the volume by 80%. The policy could be mute. There's a series of different policies that you can choose as a user. The default, I think, is a reduce the volume by 80%. So you apply the policy to reduce the volume by 80%. Volume gets reduced, and we go through and we manually we reduce the volume on all of those streams. When the communication stream is stopped, when you're done with your phone call, we go through and we find all those streams that we'd previously ducked, and we remove that ducking. We remove that reduction in volume. The volume goes back to the way it was before. So if you're listening to internet radio or whatever, VoIP call comes in, you take the call, your radio goes quiet, you're done with your call, the radio comes back on, and it all works. And this is all done under the covers for the app, so this affects essentially all the apps. Now, remember my comment about my CD player in my car pausing?
Yep.
We want to have that ability too, and that's where that notification that I talked about comes in. Apps that want to, that are doing media playback, that want to, they can actually go out and they can listen for notifications from the ducking manager. And the ducking manager will tell them, hey, communication stream just started. So they can register for these notifications and listen on them. And when the notification comes in, they can say, oh, communication stream. Instead of just letting whatever the system policy is, I can just pause. I can make a choice to just pause the video or whatever it is I'm watching. And then you'll get another notification when the communication stream is done, and then you can continue to watch the movie. That way, you're watching a DVD in Windows Media Player or whatever. Sure. It pauses, it stops. When this call's over, the movie picks right back up. I wish my TV was that smart. It would be really, really nice. And
absolutely.
So
let me ask you one quick question. I mean, how these policies, how granular are they? For example, what if could I do something like have an application where I set a policy where if I'm having a boring work meeting and I've defined what a boring work meeting is over my phone, just keep playing my video. In fact, increase the volume and pause the meeting conversation. Is there anything like that? I mean, I'm playing now, but that would be fun.
That would be fun. I don't know how I pause a meeting, though. That's the real.
I just keep redirecting the stream, so that's in a constant state of buffering
to the mid bucket. Well, we can. I mean,
that's cool.
You keep playing. Once a stream is ducked, the user can still go to the volume control, the volume mixer, and turn it back up if you want.
Absolutely.
Sure.
And once an application, say, pauses music, most likely that application will let you go and actually press the play button to start.
In fact, for Windows Media Player, if Windows Media Player pauses because of communication stream, you hit the play button, it picks right back up. The volume changes will undo that. Also, and this is a real subtle detail, when a communication stream is playing and a new stream starts, we won't duck the new stream. And the reason we do that actually is for voice narration apps. For apps that screen readers and things like that, these apps typically start a new audio stream whenever they want to read a screen element. So we don't want to interfere with these applications. So these applications, their streams will essentially override the ducking feature. New streams later on override that feature, except unless they're calling PlaySend. If they're calling the PlaySend API, which is all the dings and beeps, the new mail beeps, those will continue to be ducked when they start those.
Okay.
And that's so that your new mail beep doesn't interrupt your phone conversation.
Sure.
So,
excellent.
So I think these are really
there's one other thing I want to talk. Sorry,
Go ahead,
I'm sorry,
go
Leo.
Larry.
There are a class of applications for whom ducking is a bad experience.
Okay.
Games with voice chat, for instance. And so there is actually, one of the other things we added is an API that an application can say, you know what? I don't ever want to be ducked. Please just don't duck me ever. My game audio is really important. Don't duck me. And so an app can make a call, an API call, it's relatively straightforward, and basically say, okay, you know what? I'm opting out. I don't want to be ducked, please.
And the user has that control at a global level.
And the user has that at the global level from the top of the multimedia control panel.
Interesting.
So I'm sorry,
Yeah, so my comment was just more of an editorial one, which I think both the device heuristics, the stream switching, and the ducking are these small things that, if we didn't talk about them specifically, you might not ever really consciously notice them. This is like, once we've got this solid foundation that we built in the Vista audio system, we really got to spend a bunch of time in Windows 7 with attention to detail. And I think that's really what shows on this, is we got to take the solid foundation we built and make a bunch of improvements, which for the majority of people, I hope they don't even really notice that we did anything. It just works for them.
Excellent.
The stream switching in particular, honestly,
Yes.
I demoed that for people, and they're like, oh, that is so cool. It's doing just what I want it to do. And you know, whenever anybody says that to me, it gives me like a little warm, fuzzy feeling in my heart, because it's saying, you know, essentially you're doing the right thing. And Windows is doing the things that the users expect it to do. And anytime we can sit there and, you know, it's like, you know, you're sanding a piece of furniture and then there's a piece of raised grain. You're just sanding off the grain a little bit, just smoothing it out, taking those pain points where people, why didn't it? Mm-hmm. Why didn't it just do whatever? And we're fixing that. We're polishing the chrome and smoothing out the rough edges to make sure that, you know, people don't feel like it's not right.
Absolutely. I mean, I really don't, and it speaks to the notion of that. I really don't think Vista got the credit it deserves from an architectural, from an engineering point of view. Mm-hmm. And I think with Windows 7, it's been clear. I've been going around talking to a lot of people that, you know, it's about 95 to 98% Vista, at least at the lowest level of the system. They've done an unbelievable work in the shell, lots of changes, but at the core of the system, it's still very true to Vista and what you guys, as you mentioned, innovated on and established, and now you fine-tuned it and done some really interesting things on top of what you had done. So I think that's a wonderful
we could
truth.
not have done the things that the stuff that we did in Windows 7 to make this, to smooth out the edges, to make this a seamless, to add all these improvements, would have been excruciatingly painful, if possible at all. I'm not even certain it would be possible on the older audio architecture. The newer architecture, we spent a crazy amount of effort and time, and it was a long haul to get through that in Vista, but we laid the foundation that's really allowing us to just easily drop in new features that allow us to light up a whole bunch of new things that customers just, they've been asking for a long time. They've been, you know, or things that when we talk to customers, they're like, why doesn't it do that? Well, back in XP days, it would have been really hard to answer a lot of those questions, or to give the customers the answers they want. Mm-hmm. With Windows 7, or with the foundation we laid in Vista, we finally have the ability where we can actually say, sure, we can give you the widget that you want, because, you know, we've restructured things and we've built things on a better architectural foundation to allow us to really build out for Windows 7 and beyond, whatever we go beyond.
Excellent. So I have one last question that I have to ask. And it's really, it might not seem serious, but it is. So when you think about graphics, right, on a screen, everything comes down to a pixel, right? That's what everything is. It's what you read, you see, all the movies you watch. It's just millions and billions of pixels organized very intelligently. What's the equivalent for sound? What is the pixel of sound?
The pixel of sound is something we call a sample.
Okay.
But it's the critical thing is what's in that sample.
Exactly.
So what sampling is taking an instantaneous measure of the volume at that exact point in time. And there's this thing called the Nyquist frequency in theory. And this was invented by a guy named Nyquist in 1928 at Bell Labs, or discovered, sorry. Discovered is a better way to put it.
Okay.
And it was the basis of modern telephony. And basically what he discovered was if you sample twice as often, sample the volume twice as often as the frequency. So let's say that you can hear maximum frequency is 20,000 cycles. Actually, I can't hear that high, and I doubt anybody in this room can hear that high. But if you sample approximately 40,000 times a second, you will be able to reproduce that sound in a fairly realistic way, and that's called the Nyquist theorem. And that's the basis of this thing called pulse code modulation. And so the pixel of sound is called a sample.
Excellent.
But unfortunately, one sample of sound is not interesting to hear, because what you usually hear is a difference from one sample to the next. So it's the changes from the samples as you're listening through, as you're hearing them, is what your sense of hearing is all about. And Larry just threw that picture on the board there that demonstrates what sampling is. And
demonstrates that Larry can't draw.
That's not
That's
bad.
one cycle of a sine wave, and the vertical lines are sampling points along there. So what would be stored in a typical PCM wave file would be the values at all these points. And if this was full amplitude, if it was a full amplitude sine wave, you'd have something like this, or this would be your most negative number.
Or
And-
0.
Well, 0 is typically going to be right through the center,
Okay.
right? Oh yeah, if you're thinking of the way we store 8-bit PCM,
Yes.
that's true. But if you're thinking of 16-bit PCM, this would be 0, and this would be just saying roughly minus 32K, and this would be plus 32K. And so you take the values of each of these, store that sequence of numbers, and that's your wave file. And when you re-render those numbers through a digital audio converter, it pretty accurately reproduces that exact same analog waveform.
Excellent.
And it literally, what it's doing is it takes, when you run it through the system, and at the very back end, there's a digital to analog converter. And that digital analog converter takes a digital signal in, it takes a sample in, and it reproduces actually a voltage. So if that 0 to 32K represents, so let's say this is between 0 and
3.2.
3.2 volts, then, you know, this value is whatever percentage of that voltage applied here, and that voltage here, and that voltage here. You take that analog signal, you apply it to a speaker, that voltage moves the magnet at the back of the cone a certain amount, and that pushes out the air. And if you do this fast enough, you bet it basically reproduces the original motion of the microphone that was used to generate this, and you reproduce the sound end to end.
One thing that might be interesting to show, since we have this up there, is what was saying about the Nyquist frequency.
Uh-huh.
The theory is that if you sample it twice the highest frequency of the sine wave of the sound, you can reproduce the signal. So if this is one cycle, and if this cycle represents the highest frequency that is in your sound wave, then as long as you sample here and here at these points, then in theory you can reproduce that exact sine wave with the appropriate filtering, I suppose, on the analog side.
Or accurately enough.
Or
Accurately
to give
enough
you-
that
right.
you can hear. Yeah.
But if you sample too infrequently, you can imagine sampling exactly half as often, and your only sample points are here, then clearly a bunch of zeros, there's no way you can reproduce a sine wave out of that. So if you sample at least twice as often, you can reproduce the same.
So in the case of, we didn't really get to it, we sort of, but I'm not saying that we do that now, given that we are over time and we all have to be somewhere, but this is fun to talk about. What would HD audio look like? So in terms
Well,
of sampling, in terms
so
of...
when you say HD audio, if you're referring to the controller and codec technology that's built in on a lot of motherboards, HD audio is more of a marketing name. There's nothing HD about it. So,
Sorry.
but if you're talking about just high definition, mostly that's just talking about more channels
Okay.
of sound.
Sure.
Sometimes higher sampling rates because there's reasons why, even though in theory you can sample at just twice the frequency of the sine wave, if you sample at much higher frequencies, it's easier to reproduce the exact same wave.
Sure.
The filters involved are less complex.
I mean, you look at it right here, you can see that, you sample 4 times as often, you have that many more times. If I'm going to build the resulting curve from Frank's 4 points, I'm going to have just 4 lines. Whereas if I build the resulting curve for all the samples, however many it is that I drew out there, there's going to be a lot more points, there's a lot more opportunities, it's going to be closer. Now, Nyquist's theorem says it's good enough. It's good enough for you to be able, so that when you hear the sound, it sounds exactly perfect. You can't really tell the difference. But at some level, with some quality of equipment, you actually can, and it does make a difference.
And by the way, that's the reason why one of the reasons why CDs were originally sampled at 44.1 kilohertz, right? That's pretty close to implying that the maximum frequency is 22 point something, which is a little bit higher than the highest frequency humans can hear.
Excellent. Well, hey, thank you for this brief introduction to the mathematics and science of sound, which is really, really interesting. And of course, you guys live and breathe. So thank you very much for your great work, man. Of course.
Thanks.
All right.
You're welcome.
Quite welcome,
Thanks,
yeah.
thanks, Charles, for letting us tell our story.
Hey, I appreciate it.